Hi, this is Team Augmentors, and our final project for Intro to Deep Learning course is Learnable Data Augmentation for Consistency-Based Semi-Supervised Learning. Let's look at our motivation. Semi-supervised learning is a strong tool that uses a small amount of labeled data and a large amount of unlabeled data to achieve good performances. The existing state-of-the-art methods like fixed match and free match, which leverage consistency regularization, have made a consensus that data augmentation plays a key role in semi-supervised learning. However, selecting the optimal data augmentation method with their parameters needs exhaustive experimentation or a profound domain knowledge, which is a bit difficult. Also, augmentation methods can be task dependent. Like in the example given below, rotation is not a good augmentation operation for a task of detecting handwritten digits. Widely used augmentation policies are not effective on medical images. Thus, learning data augmentation from data is usually preferred. The prior attempts that use reinforcement learning or differentiable data augmentation are not efficient or adaptive to each class or instance. To the best of our knowledge, no method is capable of learning adaptive data augmentation policy in an end-to-end manner. Therefore, we propose learnable data augmentation for consistency-based semi-supervised learning using a method called adversarial adaptive auto-augment, in short AAAA.
Since we aim to learn the augmentation policy in an end-to-end manner, we consider dynamic online augmentation policy. Furthermore, we leverage differentiable data augmentation, where it was originally used for transforming GAN-generated images, but here we use it to learn the augmentation policy parameters. To summarize our points, we aim to learn instance adaptive online dynamic augmentation policy through adversarial training using differentiable data augmentation. Our contribution is that, first, using our learned policy, we can apply data augmentation without domain knowledge. Second, due to instance adaptive augmentation policy, we can expect better performance. For the experiments, we plan to use Cypher 10, 100, SVHN, and SDL10, but we just experimented on the Cypher 10 for now. To explain the proposed algorithm, let's start off from the baseline algorithm, fixed match. Fixed match has supervised loss and unsupervised loss. Labeled data are trained using supervised loss with its true label. For unlabeled data, they are weakly augmented to get the prediction. And then a strongly augmented version is also used to get the prediction. Using the prediction of weakly augmented image, pseudo-labels are generated and use them as a target for unsupervised loss to train strongly augmented images. So this equation shows the objective function of fixed match with supervised loss and unsupervised loss. Now this is the proposed framework. Consists of policy network, classifier, and augmenter. Policy network takes an image as an input and outputs augmentation magnitude. It is trained with flipped unsupervised loss to minimize the consistency between augmented images pairs in an adversarial manner. Whereas the classifier is trained using the loss function of fixed match to maximize the consistency between the augmented image pairs. So you can see that the policy network and the classifier are trained adversarially. This is the configuration for the augmentation that are used in the experiments. To prevent the policy network from learning aggressive transformation, we've tried adding some regularization losses. First, we tried adding discriminator to discriminate the policy augmented images. Second, added perceptual loss using the pre-trained model. Third, added label preserving loss to preserve semantic label information of the images.
We use evaluation accuracy as our matrix. Here is our baseline setting. We choose to use the Cypher 10 with only 250 labels and 4 labels as our expected lower and upper bound of performance. Our baseline method, fixed match here, is much closer to the 4 label performance. And here is the performance of our basic AAA. In the table, lower D gives worse results because the network learns more aggressively with more frequent updates. In here, the sample of our dataset, our AAA is learned too well, so it's hard to recognize them with our human eye. This is our experiment for regularization loss. Unfortunately, all of the experiments gives performance worse than our vanilla one. The most interesting part would be in the label preserving loss. Even a weight of 10 cannot influence our performance significantly. That may mean our AAA does not have the label information. So for now, we propose the AAA, and we have tried a variety of techniques to improve it. However, no one for now cannot will significantly affect. In the future, we'll still need to take more experiments to choose the hyperparameter, and we will also need to think about the design of our models.